In today's lesson, we're going to learn about 5 exponent rules. First and foremost, a number, a variable, or a product of a number and one or more variables. An example is 7a squared times b. You have, in general, this whole term 5 squared being referenced to as a power. The base of that term is 5 and the exponent of the term is 2. We're going to specifically looking at the exponent rules, and the first one is the product of powers. How this one works: if you multiply two number bases that are the same, you'll have to add their exponents. So again, if the bases are multiplied, you will add those exponents. So let's look at our first example here. We have the same base of 5, so we will add their exponents. 2 plus 6, since those are both the exponents on the base of 5, gets us 5 to the 8th power. We could evaluate that out in the calculator. That's going to be a really large number, so we'll just leave it. Next example here, we have the same bases, so we will add the exponents of 4, 3, and 1. If there's no exponent, please know that it will be a 1, so you can put that in as a placeholder. 4 plus 3 plus 1 gives us 8 y's in total, y to the 8th power here. In the next example, when you have numbers like 7 times 6, those are still going to be numbers we multiply, which would get us 42. When they're numbers without exponents, you're still going to do the same operations of multiplication like you've done for a while. Now that we have the y term, they're the same base and they're being multiplied, so we have to add the exponents on y. I get 4 by doing 3 plus the 1y over here with the 6, giving me 42y to the 4th. Next example, again, numbers without exponents, we go ahead and just multiply them like we've been for a while. Negative 3 times 5 we know is negative 15. Then must be the same base to add the exponents, so I will add the exponents on my x terms. I have 2 and then 1 over here. Since it is not there, it's still 1, giving me 2 plus 1 on my x exponent. And then on my y exponent, again, I look at the y terms and I notice that I have 2 y terms that are multiplied together, so I add their exponents. My final answer is negative 15, x to the 3rd, and y to the 13th. Let's go ahead and look at now the quotient of powers. So the quotient of powers is happening when I divide two numbers with the same base. I will have to subtract the exponents. So the opposite of the power rule, because the power rule was multiply, add. This one is divide, subtract. So I take the same bases of 6, and that's going to be 4 minus 2, giving me 6 squared. We do know that one is not going to be too large of a number, so we'll talk about what 6 times 6 is, which is indeed 36. Next example, the bases are the same. Subtract the exponents. We have y. 6 minus the exponent on the bottom, which is 1. If it's not written there, it's a ninja 1. And that gives us y to the 5th. Last example, we want to break it all up with the same bases and numbers here. I just have 10 over 15, no exponent, they're just numbers. So that's going to be a fraction like what I've dealt with before. Both top and bottom are divisible by 5, so I go ahead and divide each by 5 to get 2/3 as my simplified fraction. Then I subtract the exponents on just the a terms, which would be 7 minus 5 here. And then I look at my b terms and I subtract just the exponents on b, because I only can subtract when I'm dividing like bases. 9 minus 9. Well, 9 minus 9 comes out to 0. And then 7 minus 5 comes out to 2. So my final answer is 2/3 a squared. B to the 0 would be canceled out to 1, which is what we're going to talk about next. The zero exponent rule states that anytime I raise the base to an exponent of 0, it is equivalent to 1. Why this works is because if I have 8 squared, that is 8 times 8 over 8 times 8, because 8 squared is just 8 times itself. That comes out to 64 over 64. When I do 64 divided by 64, I know it will be 1 because any number divided by itself is going to be equivalent to 1. That's how it works, because if I use the exponent rule shortcuts here, that would be subtracting the exponents on the same basis of 8 over here. 2 minus 2 gets me 0. 8 to the 0 is 1, being equivalent to what we just did out. Let's go ahead and try 2 examples. I have an exponent of 0, and I must be taking the base and turning it into 1. So the whole base is in parentheses, negative 3x plus 7. Since that's raised to the 0, the whole thing becomes 1. But please remember that only the exponent of 0, what the base is of that exponent, turns out to be 1. So that's important for the next example, 8x to the 0 power plus 5, because the 0 power exponent is only attached to x. 8 stays, plus 5 stays. What changes to 1 is only x to the 0 power here. So it now reads 8 times 1 instead of 8 times x to the 0 power that we add 5 to. 8 plus 5 is 13. So it's so important that the 0 power only applies to the base it is attached to. In parentheses, it's attached to the whole thing. But in the second part, it's only attached to the x variable. Last 2 rules, we have the negative exponent rule. So for any non-zero number a raised to a negative exponent, we must flip the base and the power in the fraction to rewrite the power as a positive exponent. So here's our first example. I take it and put any whole number over 1, even if it has an exponent or variable. And then I'll be able to flip that negative exponent to the denominator across my fraction bar to make it positive. Let's try this first example here. 4 squared is 4 times 4. In the denominator, 4 cubed is 4 times 4 times 4. Anytime you have 4 divided by 4, it comes out to be 1. So I'm able to do 4 divided by 4 equals 1, and 4 divided by 4 equals 1. That happens twice. What is left here is 1 in my numerator, but 1 4 in the denominator. So it's positive, which is good, but it remains in the denominator. Let's try an example with variables here. We have x to the negative 6, put it over 1, because any negative exponent flips across the fraction bar to become a positive 1. X to the 6th in the denominator is my answer. For the next example, again, I put it over 1 and I flip that negative exponent across my fraction bar, leaving just 1 in the numerator. If there's moving the whole term, you still have 1 left to hold that fraction place. And then in the denominator, we go ahead and get negative 3 as my base raised to the positive exponent. So as we're going through these, it is so important that we are only adjusting the exponent from negative to positive. My base of negative 3 stays negative 3. I only adjusted the exponent to positive. Negative 3 squared is just negative 3 times negative 3, which will be a positive 9 in my denominator. So my final answer here is 1/9. Last exponent rule is that if you're raising a power to a power, you must multiply the exponent. So again, if you're raising a power to a power, we go ahead and multiply the exponents. So 3 squared raised to the 3rd power, I multiply those exponents, getting me 3 to the 6th power. Again, that's going to be a large number, so we'll leave it as 3 to the 6th. And go ahead and move on to the next example. X to the 4th raised to the squared outside of the parentheses gets multiplied to our exponent inside. 4 times 2 gets us 8 as an exponent on our base of x. Last example here, we again have y to the negative 10th raised to the 5th exponent. You multiply those two exponents together, negative 10 with 5, getting us negative 50 as our exponent on y. Now, we cannot leave a negative exponent in our answer, so we have to use the negative exponent rule we just did by placing y to the negative 50th over 1. Then, moving that negative exponent and its base to the denominator to become positive. So 1 is left in the numerator to hold that fraction bar position, and in the denominator, I move my base of y with now a positive exponent of 50 here. Can never leave negative exponents in your final answer. In the next section, power of a product, we want to find the power of each base in the parentheses. I stretched the word each here in bold, and I'll also highlight it as well, because you want to make sure you find every single base in the parentheses, the number ones and the letter ones. So the first base in the first example is negative 6. Finding that power or exponent will be an invisible 1 here. Next base is the letter x here. Again, both bases are here. We cannot combine them because they're different bases, but what we can do is step number 3, multiply the exponents of the simplified bases. So the 2 will get multiplied to the exponent 1 on the negative 6 base, as well as the exponent 6 on the x base here. From here, I'll multiply those exponents to get x to the 12th and negative 6 to the power of 2. Since this base is a number, I can actually do this math here by doing negative 6 times negative 6, which will come out to be a positive 36. In front of my x, 12. Same way to start the next example, we go ahead and find all the bases inside. The number ones like 3, as well as the letter ones like C and D. From here, we notice that we go ahead and have the negative 3 outside that will get multiplied to each exponent. Again, find those exponents. So let's put a 1 exponent on my base of 3, a 1 exponent on my base of C, and D already has that exponent of 7. Negative 3 gets multiplied to every single one. What happens here is I'm now going to have 3 to the 1 times negative 3, C to the 1 times negative 3, and D to the 7 times negative 3, multiplying every single base inside with the exponent of negative 3. From here, I actually do that multiplication, which will get me 3 to the negative 3, C to the negative 3, and D to the negative 21. As a reminder about our negative exponent rule, we can never leave negative exponents our final answer. So we always have to move them across our fraction bar. This time they're in the top of a fraction bar, so we have to move them across it. So I will make it C to the positive 3 below, D to the positive 21 below, and I can also do it with the number in front by moving 3 to the positive 3 exponent to the bottom. Now that they're moved, they go away from the numerator, and what's left is just a 1. If there's nothing left, you still have 1. I can actually do the math of 3 to the power of 3. That's 3 times 3 times 3, which would get me a 27. You multiply 3 times. C3 stays because it's a letter, and so does D to the 21. And that's your final answer. Next one, I do have things that I combine inside, so that would be the step number 2 listed above. Combine like bases that are multiplied together by adding their exponents. So let's combine our bases. 2 and 5 are not like bases, but they don't have any exponents, so you can just do it like 2 times 5, which is 10. These like bases of my x to to the fourth and x to the fifth, since they're the same base of x, can be combined by adding. So that'd be 4 plus 5, which is 9. Last one here is the y's also are like bases, so add their exponents of 3 plus 9, which is 12. Don't forget to bring down the squared, because now that I combined all like bases, I will distribute that squared to every single exponent. Don't forget that 10 is a separate base, so put an exponent of 1 when there's none written. And now I'll distribute the 2 to every single exponent by multiplying them here. So that'd be 10 to the power of 2, x to the power of 18, and y to the power of 24. How I got those exponents was by multiplying here in this case. I do have a number base that has an exponent, so I can actually do 10 squared, which is 10 times 10, and 100, x to the 18, y to the 24 is my final answer. In the next section, power of a quotient, we want to find the power of each base in the parentheses, combine any like bases that are divided together by subtracting those exponents, and multiply the exponents of these simplified bases. So what that means for example number 1 is I go ahead and again find each base inside. Looks like I have 2 different bases, one with the letter x to the power of 6, and one with the letter y, and that would be to the power of 1. Remember, when it's not written, we put a power of 1. We then multiply the exponent outside, because I cannot simplify 2 different letter bases. So that would be x to the 6 times 4 in the numerator, and y to the 1 times 4 in the denominator. Final answer will be x to the power of 24 and y to the power of 4. In the next example, I'm going to go ahead and combine my faces inside first. 6 and 3 are both numbers. Since they don't have an exponent, it's just division of 6 divided by 3, which is 2. Because the letter B's are both in the top and the bottom, I can simplify them with subtraction first. So I'll subtract b to the 7 minus 3 as I'm subtracting their exponent powers. Don't forget, you still have the power of 6 raised outside. Inside, the 2 will stay, but I know the exponents of 7 minus 3 will make 4 as an exponent on b. When I'm going to go ahead and multiply the exponent inside, I got to make sure I do it to the b and to the exponent on 2. Remember, when there's no exponent written, we put a 1, but it has to go to every single number base and every single letter base. So that would be 2 to the 1 times 6 and b to the 4 times 6. b to the 24th is going to be my answer for the letter base, and 2 to the 6th is going to be my answer for the number base. I can simplify 2 to the 6 down by doing 2 times 2 times 2 times 2 times 2. So multiplying 2 6 times, that's what the exponent means. It tells me that I have 6 2's there. And that goes ahead and comes out to be a 64. So my final answer is 64, b to the power of 24. Next one, same thing. I want to simplify the bases here. Again, when I have numbers without exponents, I can just do their division. So that would be 4 over 8. That's a fraction. Think about simplify fractions by knowing that I can divide the top and bottom by 4 to get me down to 1/2 here. That's what I'm write as my answer, 1 in the numerator and 2 in the denominator to represent that 1/2. The letter A's can also be adjusted here. As I see, I have A to the first power. Again, when there's no number, I put a 1. And I have A to the 4th power as well. When I do A1 minus 4, I'll get my answer for that base of A. Then I do the letter B's here. As you see, I have B to the 7th and B to the -1. I will do that subtraction because I have to subtract your exponents here. From here, what I do is actually do that subtraction of my like base exponents. So I go ahead and keep the 1/2 out in front, but I do the subtraction of my exponents on a. 1 minus 4 comes out to be a -3. Then I do the subtraction over here, but when I subtract a negative, we know that turns positive, so that would really be b to the 8th here. And I have it to the power of 2. As a reminder, that goes to every single exponent. The exponent on b will be multiplied by 2. The exponent on a will be multiplied by 2. Don't forget 1 and 2 are both exponent bases. They're bases, so they need an exponent. So I will also multiply the 2 to the exponent on the denominator of 2 and the 2 to the exponent of the numerator 1. So what this looks like is like this. I'm going to have 1 to the power of 1 because there's that hidden 1, and it will be multiplied by 2. I'm going to have in the denominator here a 2 to the power of 1. That will be multiplied by 2. A to the power of -3 will be multiplied by 2. And then b to the power of 8 will be multiplied by 2. From here, I'm going to go ahead and actually do the multiplications of my exponents. So that's going to be 1 squared, 2 squared, because 2 times 1 is 2, and the 1 squared comes from 1 times 2 is 2. And then we have an a to the -6, because -3 times 2 is -6. And b to the 16, because 8 times 2 is 16. From here, I'm going to clean this up a little bit here. I know I have a fraction in my final answer because I have to do 1 squared here, which was 1 times 1, 1. 2 squared would be in the denominator. That's going to be 2 times 2, which is 4. Careful with your a's and b's. When you have a positive exponent, it goes in the numerator here. So b to the 16 will be up top. But in my denominator will be where I have to move my a to the -6 to no longer have negatives in my final answer because there's not allowed. And it would be a to the +6. So my final answer here is 1b to the 16th over 4a to the 6th. Last example, same thing. You want to simplify what's inside first. So I see that I have like bases of r. Subtracting the exponents on those bases, it will be r 3 minus 1. That's the exponents, top to bottom subtracted. Next base is the letter s. Simplify the inside first here. Letter s will be 5 minus 6. Again, subtract the top exponent from the bottom. Last bases that are the same are t. I can subtract the exponents on the same basis. And then don't forget the -3 outside, but let's actually do those subtractions on the exponents to get r squared, because 3 minus 1 is 2, s to the -1 power, because 5 minus 6 is -1, and t to the 0 power, because 2 minus 2 is 0. As a reminder, anything to the 0 power comes out to be 1, so that actually will just become a 1 here. And just so you know, in general, anything that's multiplied to 1, regardless if it's a number or a letter, just stays itself. So I can actually erase and get away with that 1 being gone. From here, I multiply the -3 to each of these exponents here. So it'd be r, that's my first base, with an exponent of 2 that will be having to multiply by -3. S is my next base, that's to the -1 power, and -1 will have to be multiplied by a -3. From here, we go ahead and actually do the multiplication to get r to the -6, because that's what 2 times -3 is, and s to the 3rd power, because that's what -1 times -3 is. This is not my final answer because I cannot leave a negative exponent. What I have to do is I have to keep S3 exactly where it is in the numerator. Because it's a positive exponent, it will go up top of our fraction. When it's a negative exponent, and it's in the numerator already, you have to move it across the fraction bar to make it a positive exponent, so it can only be a positive exponent r to the sixth when it's located in your denominator. So s to the power of 3 over r to the power of 6 is our final answer.